Hi folks, today I'll be presenting the paper The GAN is Dead, Long Live the GAN, which is a modern baseline GAN. So what's the motivation? So traditional and many state-of-the-art GANs often suffer from two problems, mode collapse and training instability. And the current most popular GAN, which is style GAN, have accumulated a lot of tricks to actually solve the above mentioned problems. However, they still do not achieve full mode coverage. And they use the original loss function from Goodfellow et al., which in theory shows convergent properties, but in practice is very difficult to optimize due to its minimax nature. And what this traditional loss function does is it encourages G to just fool D on the subset of the whole variety of dataset, and it forces D to use a single decision boundary since real and fake data are considered in isolation. So to understand these two problems in depth, let's use MNIST dataset as an example, where G's job is to produce digits and D's job is to catch the fake digits. Now assume D's weak spot is distinguishing between real and fake 7. G then tries to naturally exploit this weakness of D by generating a fake 7 and uses it as a shortcut to win the minimax game, which is what mode collapses. Now, since D is not a constant, it trains itself to eventually spot a fake 7 until after that, G then tries to exploit other modes in the dataset, like ones, for example, and then D tries to catch up with that. And this cycle goes on, which is what non-convergence is. So, what's the solution? We introduce a new loss function. So, the paper proposes a new loss function which is inspired by relativistic pairing GAN or RP GAN, which looks similar to the original loss function. The only difference is here the discriminator's output on fake samples and real samples are coupled together, and such that the fake sample is always critiqued by its realness relative to a real sample. This allows to maintain a decision boundary in the neighborhood of each real sample. So let's use the MNIST example again to understand this loss function. So let's assume G is trying to exploit D's weakness of distinguishing real and fake 7s by generating a good fake 7. However, this time D compares realness of fake 7 generated by G with the realness of real 4. And in this time, D says this fake 7 actually looks bad in comparison to a real 4. This forces G to do the real work, which is learn to generate all 10 digits so well that they can be side by side compared with any real digit. Thus, this solves the problem of mode collapse. However, there is still the problem of non-convergence. So we add regularization to the loss function, where R1 and R2 are basically zero-centered gradient penalties to allow convergent training. R1 penalizes gradient norm of D on real data and R2 does that on fake data. And the key idea over here is when G already produces P theta equals PD, we want the gradient of D equals to be 0 so that G is not pushed away from its optimal state and training doesn't oscillate. So the final loss function looks like this, which is a combination of RP GAN plus R1 plus R2 gradient penalties, which is also called the R3 GAN. And the second part of the solution is a new baseline architecture. So we use this table as a roadmap to understand how the final architecture is constructed. So they start off with the style GAN, they strip the style GAN off with its different features and tricks. They add the new loss function, which we just discussed, and they modernize the architecture using convnext, which is a ResNet. And this is how the original architecture of style GAN is simplified to a simple architecture. So let's talk about the results. So let's see how the two problems are solved, which are non-convergence and mode collapse. So in this diagram, we can see that when we use regularization penalties, we can achieve non-convergence. We can solve non-convergence. And when we use the RP GAN, with a combination of regularization penalties, then we can achieve full mode coverage. R3 GAN also outperforms style GAN methods and recent diffusion based methods in terms of FID score on multiple data sets. The only other time when a GAN model is able to outperform R3 GAN is the ones which had ImageNet feature leakage, where the discriminator of these models consists of a pre-trained ImageNet classifier which can leak ImageNet features into the model. And FID is calculating using pre-trained ImageNet classifier. So naturally these GAN models were able to achieve a lower FID score. However, R3 GAN still outperformed all other GANs in terms of KL divergence and in terms of recall. Now, despite R3 GAN having competitive FID scores, the authors still claim that their original intent was to just provide a simple baseline which can serve as a possible backbone for future GANs. And I'm just going to end the video by showing some examples of generation from the original paper. Thank you everyone.